Okay, time to get going. So last time we just finished up talking about vector fields and things that we're going to eventually see that you can do with vector fields, and that was chapter 3. Moving on now to chapter 5, and so you may be wondering what happened to chapter 4. Right. Chapter 4 is cool material, very important. But it is the only material in the course that isn't part of what I'll call the prerequisite trail for Chapter 6 and 7. And Chapter 6 and 7 make use of kind of everything that comes before, except for Chapter 4, and that's somewhat debatable in terms of how much you use it, do you really need it, and stuff like this. So why is that relevant? Well, as you all may have heard, rumor-wise around campus, but the last part of multivariable calculus is the most challenging. That's where there's the most ideas that connect in the most different ways, and it's geometrically, there's geometric visualization challenges, and there's just a lot to do with Chapter 6 and 7. It's a big deal, and it's that's where it gets the most interesting, one could say, but definitely the most challenging. So I think it's a really good idea to get to it as fast as possible, so that you can have as much time as possible from when you learn it to when you're tested on it, right? And so pushing it forward, pulling it forward to as early as possible in the course is very valuable. So of course, anything I pull further to the front of the course, something else is going to have to go to the back of the course. I can't push to the back of the course anything that's in the prerequisite trail of that material. So we're left with only Chapter 4 that I can push back. Okay, so we will get to Chapter 4. It'll just be at the very end of the course, and we're going to proceed with Chapter 5. Okay, now y'all remember partial derivatives. What was it, a week or two ago that we first started doing partial derivatives, and I made an assertion at the time that, look, they're convenient and all, but these are not the end-all, be-all of differentiation, and really it shouldn't even be your fundamental point of view on differentiation, and I hope that that's become clear now, that ultimately a derivative is how you turn an input change vector into an output change vector, right, most generally, and what turns an input vector into an output vector? A matrix, right? So the derivative matrix, df, that's what a derivative really is in a multivariable setting. And partial derivatives, again, a convenient foot in the door. But, you wouldn't want your understanding of multivariable derivatives to just be partial derivatives. That's really not good enough. Okay, so in the same way, I'm going to start, as the book does, with a point of view on multivariable integrals. That's really not the best way to think about it. It's got a problem that we're going to notice pretty early on here. Nevertheless, it is really convenient, and it's an easy foot in the door, and we're going to get one to the win column, right? And it will have value going on down the road as well. Just like partial derivatives, they have their uses. Anyway, the reason I bring this up is, again, I don't want you to think in terms of that what I'm about to show you should be your cornerstone point of view on multivariable integrals. It shouldn't. This is just a first attempt. Let's think of it that way. Okay, so here is a flashback to Calc 2, probably, I suppose, depending on the order your course covered them in. But the idea is if you have a curve and then you rotate that around, let's say, the x-axis, the result then being a surface, and you could ask reasonably how much volume is there inside of that surface, right? And the idea is that you can first chop that up into a bunch of little pieces. Let's see, nice thin little pieces. I hope I can get nice thin little pieces there of volume dV, right? And each one of those little dVs I can compute that total volume by looking at the cross-sectional area, and that's just the area here, right? Just that area, and of course that's the area of a disk, right? This is a barnyard variety geometric figure. It's a disk, right? Super easy to write down the formula for that area. And then we multiply by the thickness. Let's see here, what would be a good contrasting color here that I have? I guess I'll use red. There's a thickness, right, that is dx. And altogether then, the volume that we're interested in, the thing that we're going to sort of integrate, if you will, from A to B, is that formula right there. And I hope this all looks familiar. Volume of a rotated surface, pretty standard application. We're going to kind of rip off this idea and take our first step into multivariable integration. And the idea, the big part of this that we're going to steal is this business right here, that a cross-sectional area, here we go, cross-sectional area times a thickness gives you a volume. All right, is everybody on board? All right, so let's do it. Here's what we're going to do. Here's a graph of a multivariable function. Keep in mind a graph, because we're setting z equals, right, to the value of a function. We have height as a function of location in the domain. So that graph is a surface. Let's ask now, not a rotation, but if I wanted to compute the volume under that graph. Right? Okay. How would we do that? Well, let's slice it up into pieces like we did previously. We can talk about how much volume there is in this kind of slice, if you will. Right? That amount of volume there. Which is this over here. And how would I compute this volume? And of course it's tempting to say, I'll just multiply the cross-sectional area times the thickness. And the problem is that cross-sectional area, this is no longer a barnyard variety, garden variety, geometric shape. It's not a disk, it's not a square, it's not a equilateral triangle, side, it's not really it's not a thing, right? So a lot of people would throw up their hands at this point and say, well, we're dead in the water, we can't proceed. Oh well. But let's press on anyway. And in fact, this area is actually an area that I claim we've seen before. This cross-sectional area, here it is. So that area right there, it's the area under a curve. Here's the curve. Right, that curve being a cross-section of our original graph. Area under a curve, where have we heard that phrase before, right? Of course, that's what integrals compute, right? So there's a temptation to say, hey, it's area under a curve, boom, let's just write down an integral. There is a little asterisk we do have to worry about. I've warned you all about this before. If you want to compute area under a curve, you better make sure that curve is the graph, right, of something. It's got to be height as a function of location. And is this curve equal to that? Well, I mean, here's the equation. I mean, after all, this is part of our original surface, our original graph surface. Notice, though, for the purposes of this conversation, for the purposes of trying to compute that area, I have to be clear about which area I'm interested in, right? There's a bunch of different cross sections. Which one am I interested in computing the area of? Said differently, I have to choose y. Said differently, y has to stay put while I'm computing the area for that particular value of y. Said differently, while I'm computing this integral, y is a constant. And that means that what we actually have here, if you look carefully at this curve, we have let's see here, height z as a function of, well, there's really only one actual variable, and that is x, which goes from A to B. So I have height, vertical height as a function of horizontal x. That's a graph. So, yay, we win. This cross-sectional area is an integral. This area right here is that integral right there. How are we doing? We okay with that? Now this creeps a lot of students out, including myself when I was young. I look at this and I say, well, this is an integral dx. Okay, that's cool. I know how to do integrals of f of x dx. There's a bunch of formulas and stuff. What do I do with this y? What is an integral of y dx? Is y, but see, y isn't height or anything. Normally y is height. Normally y is a function of x. It's not a function of x here. What do we do with it? The answer, no problem. We've already addressed that. Y is constant. This y we're going to treat as if it's a constant. Treat it like a k. Because again, very importantly, for this entire computation, computing this cross-sectional area, it is literally not allowed to change. It is literally a constant. Does that make sense to everybody? So it's an illusion. If we look at this and think that there's two variables inside of that integral, no, there aren't. There's two letters of the alphabet that are kind of late in the alphabet that we think of as being variables, but y is a constant for this integral. So no problem. And everything proceeds as before. We know how to compute cross-sectional area, right? And we were interested in computing the little slices of volume. Let's see here. I guess I used purple. Yeah. Okay, so these little slices of volume right here. Right. Area times thickness. Right there. Area times thickness. What we're going to do with these little pieces of volume anyway. Oh, I missed. Look at that. I'm sorry. I missed the... There we go. What were we going to do with these little pieces of volume? Well, we were going to add them up. Right? We're adding up all the little volume slices, and each volume slice is an area times dy, which is an integral times dy, and here it is, integral times dy. Everybody cool? Now this is confusing in a couple different ways because we're doing two different integrals. Right? There's integrals happening here in two different directions. And I'm just going to clean up the mess here because this has gotten out of hand. On the one hand, we're integrating in this direction and looking at area times thickness to give us volume. On the other hand, we're also, for any given value of y, we are integrating in this direction. We are integrating height times x thickness to give us that cross-sectional area. Is everybody on board? All right, so then you look at this expression right here. This is called an iterated integral. The idea is that it's an integral of an integral, which feels like an iteration. This term also has kind of always bugged me. But I feel like, to me, an iteration means you do the same thing repeatedly, right? And very importantly, these are not the same things. We're doing an x integral there, and then a y integral there. They're not the same. So I put in about 20 years on trying to change the terminology of this by trying to popularize what I think is a better term, nested integrals, right? It's an integral inside of another integral. Right? I think that is more sort of honest, but have not made a dent in the norm. So iterated integral is the term. You're going to probably hear me say nested integral here and there. That's an old habit. Okay. All right. So now a few things to keep in mind. There is an awkwardness. Oh yeah, I'm sorry. Question.
Is the x constant in the outside integral?
there is no x in the outside integral. So here's the outside integral is dy, right? The integrand is this expression right here. But once you compute this expression, the x, I'm going to say, integrates out. Right? You'll see that happen in the first example we'll have here. Yeah, that's right. So that's there are no x's left. Yeah. Okay, so terminology. It's tempting to refer to these integrals as, well, there's the first one and there's the second one. There are two of them, so why not first and second? The problem is that as we constructed this integral, the dy integral was written first. Right? And then the dx integral was written second as our part of our construction process. But how are we going to compute this thing? We're going to have to start with the dx integral. I can't start with the dy integral. I don't know what my integrand is for my dy integral yet. Right? The only way I can know my integrand for my dy integral is to have already previously done the dx integral. So the dx integral has to be first when it comes to computation. So first is ambiguous. Do you mean first in the slicing process or first in the computation process? This, I think, is a nasty little problem. Causes confusion. There's an easy way out, and that is I will refer to the dx integral as the inside integral. I think that is unambiguous. And I will refer to the dy integral as the outside integral. And I encourage you to adopt similar terminology. Again, just because otherwise your listener doesn't know what you mean, which is the purpose of words, right? Okay. All right. Okay, another point to keep in mind. And once you've got an iterated integral looking at you, it is easy to kind of lose track and forget what happened, where did this come from, and thus, how do I treat what's going on? Easy to forget, but when you're doing the inside integral, when you're doing that inside integral, whichever one is on the inside, that outside variable is to be treated as a constant. And, well, of course it is. It is literally a constant for the purposes of defining what that inside integral is. Is that cool? Right? So not in all instances will you have a picture sitting there looking at you. So you just need to be prepared. Just remember the inside integral, the outside variable should be treated as a constant. Everybody's happy? Let's crank one out. Let's compute the volume under this graph. So function given, graph makes a surface. We're going to look over a certain rectangle. This is the rectangle in question. By the way, let me talk about that notation. Very handy notation. If I want to describe a rectangle in the plane, notice the rectangle is determined by what is its shadow over here on the x-axis and what is its shadow over here on the y-axis. And so we use this kind of times notation there to represent that resulting rectangle. Does that make sense to everybody? It's a good one to be aware of. A very common notation. I'll be using that notation a lot in this class. Okay. So, well, we've already developed the strategy previously. We don't need to go through that whole process again. We have established that if you want to compute the volume under a graph, iterated integral, right? dy integral of a dx integral. So, boom, we write that down. And now let's see here. We take them inside out, as previously discussed. So let's talk about this inside integral. We need to compute. We need to do some antiderivatives. Now, here's where a lot of students will mess up. It is perfectly reasonable and normal and familiar to look at that x squared and think, okay, the antiderivative is 1/3 x cubed. Cool. And then to think, okay, let's look at this y squared here and the antiderivative of that. And a lot of students will say 1/3 y cubed. Easy mistake to make. Right? But you've got to remember, and this is really, really important, the outside variable, you have to remember to treat that outside variable as a constant. It is literally a constant, right? And so you have to treat it as such. So that y squared, don't follow your Calc 1 anti-differentiation rules. That's just constant. And the antiderivative of constant is constant times x. Is that cool? Okay. That's the first landmine. There's only really one other landmine here, but this is another one that is pretty easy to step on. So let's see here. The values here, 0 and 1, are what we plug in. And what do we do with those values? Well, the 1 gets plugged in. And a lot of students, again, not being sufficiently wary, will also plug in the 1, right? The value that we're plugging in for x, we'll actually plug it in for y also. That doesn't make any sense. Y is not ranging between 0 and 1. X is what's ranging between 0 and 1. Y is constant. It's just y. It just stays y. Right? So don't make this mistake. Again, super easy to, if you're just a little bit too casual, right? A little bit too sort of just kind of blowing through it, you might accidentally make that mistake. My personal little hack to avoid that landmine is this right here, where I will actually indicate as I'm writing, right, which variable it is that takes on the values in question, right? So we've got 0 and 1. Instead of just putting 0 and 1, I put x equals 0 and x equals 1. And that's my little visual reminder, so that me 5 seconds later, who might have forgotten what's a variable and what's a constant, will have that visual reminder and thus not plug it into the wrong thing. Yes?
Wait, so the inside isn't always dx though, is it? Or it is?
Well, all we've done right now is with dx on the inside, dy on the outside. We'll get to the doing it the other way in a second.
Okay.
For the moment though, dx is on the inside because that's all we've justified.
Can you justify it again?
It's this whole slicing volume cross section process. I mean, that's a long discussion. But don't forget this is all being recorded, so you can listen to it again. Right. Okay, how are we doing? Is everybody all right? Okay, so, it's all downhill from here. You plug in x equals 1 into here, and it becomes this, right? And then you plug in, let's see here, you plug in x equals 0 into here, and it becomes this. And then you subtract, and you notice that the y doesn't disappear. The y is still in it. The x disappeared. We plugged in constants for it. We plugged in 0, plugged in 1. Right? The y is the y, still there. Well, back up to the picture. The y is supposed to still be there. That inside integral, just as a reminder, let's see here, the inside integral is telling you cross-sectional area as a function of y. It's supposed to depend on y. How much that cross-sectional area is depends on what value of y do you take that slice. So again, all as it should be. Everybody good? Okay, and now the evaluation is something that y'all are all experts at, computing this integral. Right? It's just it's literally a single variable integral. Okay. All right. Okay, so keep in mind, I motivated all this by I wanted to compute the amount of volume under a graph, right? This is what we were originally looking at, is this volume right here. And I arbitrarily chose to make my slices like that. Well, it's totally arbitrary. I didn't have to do it that way. What if I had decided to chop up, where's the arrow? Oh, here it is. What if I had decided to chop it up differently? Let's see how good my freehand art is. What if I had decided to chop it up into slices that look kind of like that? Right? And then look at all of those slices for all of these different values of x between a and b. And then how would I compute the areas of those slices? Well, for each individual slice, I would be doing an integral as y goes from c to d to get my cross-sectional area as a function of x, where x is a constant. Anyway, you put it all together, following exactly analogous to this argument here, right? And what you will find is that you get this right here. You get this right here. So previously, we walked through and talked about how volume can be computed by that integral on the left. And I'm going to leave it as an exercise for y'all. I think this is a good, healthy exercise. Step one, make sure that you understand this argument. Right? Think it through. Rewatch the video if you have to. Make sure you're comfortable with what happened here. Right? And then just think through strategically the same approach, but just slice it in the other direction, and you'll end up with this as your result. Computing the same volume. Okay? So, yeah, question.
Will it ever be smarter to do the derivative route?
Yeah, that's right. It depends on, there's a bunch of little detail devils. So you'll notice in here, I had to do the x antiderivative first. There. I'm sorry?
In this case, it doesn't really matter.
In this case, it doesn't matter. Yeah, in this case, it's just as easy either way. But if this function were, there are some annoying examples where the x anti-partial is hard, right? But if you switched it, do the y anti-partial first and subtract, then algebraic good stuff happens that makes the x anti-partial doable. So yeah, sometimes it does matter for convenience, but it's just a matter of convenience. Yeah.
Is there a reason why we don't use partial notation?
I mean, it's just norms. I hear where you're coming from. Yeah, there's a case to be made, but it really is just a notational thing, and so I don't think it's worth worrying about. Yeah, it's a good point. Okay. Yeah, so nice exercise. I want to encourage everyone to actually take out a sheet of paper at some point and make sure that you can do that. It's, like I say, good exercise. The punchline is that you can switch the order of the differentials, and it's all good because you're still computing the same thing. But do keep in mind, now here's another landmine. The dy integral has those bounds. So if you move what had been on the outside to the inside, you have to move its bounds too, of course, right? So outside sticks with outside. The range of values for y is still the range of values for y, and if you move the differential to the inside, you got to move it down to the inside. So make sure to, when you switch differentials, do it like this, right? Don't do this. That's no good. Not allowed. It doesn't make any sense. Okay. All right. The other little warning I'm going to give you is that this only works for rectangles, which seems like a silly observation because the only things that we've done so far were where the domain is a rectangle. We are soon going to be talking about what happens if your domain is not a rectangle. And when your domain is not a rectangle, there is no version of switching differentials and just for free, just kind of switching the bounds. No, everything becomes different. It can still be done, but everything becomes different. So this special case where you just switch the differentials and the bounds is peculiar to rectangles. All right. Okay, so here's a subtle discussion, but really, really important. When we were doing single variable calculus, we computed, area under a curve, right? Area under a graph. Wrote down a Riemann sum, right? And found some rules about antiderivatives and stuff like that. And you compute area under a graph. Great, cool. And then it was pointed out, yeah, you can compute lots of other things too. You can compute the amount of mass in a one-dimensional rod along the x-axis, or you can compute the amount of work it takes to perform a task, or you can compute the population of bacteria in a petri dish. There's a million little applications, right? Same integral that we use to compute area under a graph. Just lots of applications. Tempting then to say, okay, well now we can compute the volume under a graph surface. Maybe we can use the same integrals to compute, let's say, not a one-dimensional mass distributed across length, but a two-dimensional mass distributed across an area. Why don't we just write down the same thing, right? I mean, this here allows me to add up a bunch of slices of volume. Why wouldn't this here allow me to add up a bunch of slices of mass? So it would seem, right? And it doesn't work. As an argument, it doesn't work. As a result, it's going to turn out later, we're going to find that this will actually give you the right answer. But for reasons that we are not ready for yet, as an argument, it doesn't work. Let me point out what the problem is. This right here, when we were computing volume, right? The F represented height. The dx represented length or width or whatever you want to call it. And so, okay, we're interested in computing volume. We have height as our integrand, and well, height times length. Oh, yeah, sweet. Height times length, that's a thing. We already know what that is. That's area. Right? And then we were able to make arguments about area because we know what area is. We understand how area works. And so, for example, up here in this picture, I can talk about little pieces of area like this, and I can make geometric / intuitive arguments about how, hey, this total area is the sum of all those slices of area, and I can make that statement because I understand area. That's a thing. We have an experience with it. Okay, now let's try to do that down here, and inside of this integral where we've sort of naively just, kind of like in single variable, let's just put density in there. This would be mass per unit area in this case, and let's see if it works. And okay, so that mass per unit area, the mass after all is distributed over an area, and we will multiply by length, and let's see here, mass per unit area times length, okay, let's say mass per unit area times length. That's not right. I don't know what that is. Mass per unit area times area, I understand. But mass per unit area times length, it's not like there's a cancellation. I guess I could say this is mass per unit width. But that's not something I have any previous experience with. Does mass per unit width kind of accumulate like area does? I don't know, because I don't know what mass per unit width is. So we are dead in the water. We just can't proceed with this. Does that make sense? Everybody ever see the problem? Argument fails. Okay. All right, so that's a real disappointment. This is one of the big problems with iterated integrals. This is why I say iterated integrals are, they have their moments or they have their uses, right? But they are not sufficient as an end-all, be-all approach to understanding integrals. So we have a problem, and we're going to have to figure out how to deal with it. All right. Okay, let's talk about double integrals. New idea. Now, before I go into this, I want to remind y'all about single variable integrals. Here's the definition of a single variable integral. It's a Riemann sum, right? Single variable integral is a Riemann sum, like so. Bunch of details to be worried about. Y'all may recall Riemann sums from a long time ago. I had a misimpression when I was in high school learning calculus. I somehow had it in my head that Riemann sums were the old way of computing the area under a curve. That got completely outdated when Newton came along and discovered the fundamental theorem of calculus. And now we would just use f of b minus f of a. We'll use the fundamental theorem to compute the area. And why would anyone ever do a Riemann sum? Right. Well, here's the thing. And quick little historical note: if the Riemann sums were the outdated thing that Newton replaced, how do I square that with the fact that Riemann wasn't even born yet when Newton came up with the fundamental theorem of calculus, right? So I was pretty far off, right? Just chronology-wise, if nothing else. So the important thing to understand is that Riemann sums are a definition. This is what an integral fundamentally is. A lot of people mistakenly think that an integral is area under a curve, and that fundamentally, definition, at its most basic level, an integral is area under a curve, and it's not. Area under a curve is a kind of useful visual aid, I suppose. But it's not a definition. It wouldn't be useful as a definition. And furthermore, there'd be pretty severe problems with using it as a definition. We need Riemann sums to be the definition. Now, why do we need Riemann sums? I'm going to try to exercise some restraint here, and not. I could totally spend half an hour on this problem, and we just don't have that half an hour. But I'm going to point out, if you go to my YouTube channel, and if you let's see, it's called Miscellaneous Topics is the name of the playlist. I have a recording, about a half an hour, called "What is an Integral?" or something along those lines, something about integrals, and I go on at great length and in great detail about why it's important that integrals be defined as Riemann sums. And the very short version of this, and again, I wish I had time to go through this, is that Riemann sums are something that you can directly connect to applications, such as mass. Well, I suppose I want to compute the mass, again, on a one-dimensional rod, right? Y'all have all seen that example back in Calc 1 or Calc 2, one-dimensional rod, and you chop up that one-dimensional rod into little pieces, and on each piece, you can talk about mass per unit length times length on each little piece, and then you add up. You do a summation over all those pieces, and then you take a limit as n approaches infinity, right? And there you go, and you've constructed a Riemann sum. And you can do that for a mass problem or various other different applications. You can chop that question up into little pieces, answer the question on each little piece, and then add up over all the pieces, namely Riemann sums. Okay, now that said, why can't we just do the same with area? And I emphasize now, let's pretend that there were no Riemann sums. Let's suppose I had defined integrals as being area. How would I connect mass to area? Is mass just obviously the same thing as area? No, of course not. Well, what is it that, if you're going to say mass is area, you've got to justify that. Where'd that come from? You can't just assert that that's true. It's got to be clearly true for a reason. And frankly, there is no good justification of this. You can't do it. There isn't such an argument. Or to whatever extent there is, any such argument, frankly, is kind of this. right? And people will talk about, well, you can take a mass and you can kind of chop it into pieces, and each height you can think of as being, or each density you can think of as being a height, and each blah, blah, blah. They're basically constructing a Riemann sum and then reinterpreting that Riemann sum as an area. Which means you're using Riemann sums. We still don't need area. That's part of the argument. Does that make sense? Okay, so the big point here is integrals are Riemann sums, and so when we say, well, we're going to generalize now, we're going to try to do something called a double integral. I'm going to try to come up with a definition of, kind of like the definition of a regular single variable integral, but I'm going to try to make it multivariable. Riemann sum is what I need to mimic. I need to model Riemann sums. And the geometric application is that's curiosity. It's not really relevant to the definition. Okay, all right, that's enough of that. Okay, so here we go. Here's our interval from A to B on the x-axis, and what I like to call chop it up, add it up strategy on that interval. And so again, you take that and you chop it into little pieces. And then on each little piece, each individual little piece, whatever question you're interested in there's some function that you can multiply by the size of this little piece to get what you're interested in. So for example, if this is a metal rod and we want to compute the mass, then on this little piece here, on that little piece, I would multiply mass per unit length times length. And that would give me pieces of mass. I would then be adding up little pieces of mass. And that gives us our total mass. Notice no area anywhere in this picture. Various other things that I could chop up into little pieces. Integrand is whatever it needs to, whatever is the thing that you multiply by size to get stuff. That's what the integrand is. And then you add up. And so this construction is the answer to lots and lots of single variable calculus questions. And that's why integrals are cool, because we can chop everything up into little pieces and then add up like so. So we're going to try to mimic that now. And here's what it looks like. Let's see, here we go. If I have a rectangle, and on that rectangle, I want to do a chop it up, add it up strategy. If I want to say, look, I'm going to look at one little piece at a time, little piece like that. On that little piece, let's see here. If mass were distributed over this, then I would take mass per unit area to be my F, and I would multiply by area. And there's nothing weird about that at all. Mass per unit area times area, mass. I know what that is. I understand mass. We have physical intuition for mass, and so no problem. Right? If this were, the state of Wyoming, right? And I want to compute the total population of Wyoming, then on each little piece, each little, county-like thing, I would say, okay, population per unit area times area gives me population. And then I would add that up over all of the little pieces. Okay. Does that make sense so far? Okay. All right. So this is the big idea of a double integral. We're just, again, it's just kind of an adaptation of the single variable idea. But size is now area. So that's a little different. It's area instead of width. We're adding up in two directions. I is going to go from 1 to n, but also, furthermore, j will also have to go from 1 to n, because I have to add up. It's not good enough to just add up a column of little squares, right? Or to add up just a row of little squares. For each value of I down here, I've got to go all the way up and thus use all the values of j. So a regular Riemann sum has n terms in the summation. Our new kind of Riemann sum has n squared terms in the summation. So that's weird. Okay, there's a bunch of little detail doubles to be worried about. Let's see here. We have, let's see, in this slicing process, as you slice perpendicular to the x-axis, right? Notice you are also literally slicing up the x-axis, and all of that discussion, that goes all the way back to single variable calculus, delta x b minus a over n, x of I is a plus I delta. That's old news, right? Y'all have seen that before, long ago. But now we just also have to slice perpendicular to the y-axis. Oh, come on, I can do better than that. Yeah, close enough. So slicing up perpendicular to the y-axis, thus giving me my little sub-rectangles, right? My little pieces there. I'm slicing up the y-axis, and that gives me a delta y formula and a y sub j. And it's just details, right? But that's how those details work out. The punchline, though, is I'm going to be adding up like I have here. Everybody happy? All right. Okay, so definition then. This is what a double integral is. This expression that we just constructed here, that is our definition of what we call a double integral. Now the notation here for a double integral is just notation. Double motivates having two little integral symbols there. Why do we have two little integral symbols? Well, the best answer to that question is going to come later on this page. But you could say it's because this is a two-dimensional domain, right, instead of just a one-dimensional domain. Notice that I'm using kind of a shorthand here, delta x, delta y. I'm writing that as dA, right, representing a little piece of area. Because importantly, right, that's what delta x, delta y's job is to be the area that I multiply by whatever the integrand is. So I think the notation's pretty plausible. Now, the book has something similar to this definition in it. The book, though, makes it significantly more complicated. Was that a... Yeah, go ahead. Yeah.
Does this definition only work for rectangles too?
Yes, this is only for rectangles. Yeah, we'll talk next time about what to do if it's not a rectangle. Yeah. So the book takes this arguably more seriously. They don't assume regular partitions. They allow irregular partitions. They don't assume that we're always looking at the right endpoint, top right endpoint of it. Allowing for possibly choosing different test points and irregular partitions makes their definition more robust. It makes it more mathematically powerful, and we will not have any use for any of that in this course because we're only going to deal with functions that are continuous, and when the functions are continuous, these don't make any difference at all. Right? So now if you take Math 431 or Math 531, something like that, then yeah, you're going to have to worry about irregular partitions and arbitrary test points, and it matters, and it does make a difference. And if you insist on doing it the way we've done it here, big problems, right, in Math 431, Math 531. It's not a problem in Math 219 or in the real world that y'all are going to experience. Okay. All right. So yeah, let's revisit the volume under a graph question. Let's see here. How are we doing? Oh, I have 15 seconds. You know what? Let's not. Whoops. We will draw the line. Whoa, where am I? Oh my gosh, here we go. Okay, drawing the line right here. Okay, y'all have a good rest of your Monday. See you on Wednesday.